Okay, today we are going to talk about CTL model checking. As a new student, you probably already have some basic knowledge of computer science, but you might not be familiar with what model checking is or what it is used for. So before we dive into today's main topic, let's first introduce some background knowledge to get us all on the same page. So in our daily software development, we always want to make sure that there are fewer bugs in our program. But besides submitting our code to compilers to check for errors, we can also use various formal verification tools to prove the correctness of our code. So some of these tools utilize model checking techniques. And this approach models the program as a finite state machine and uses mathematical logic, especially temporal logic, to describe the system's behavior and properties. It then automatically verifies whether the system satisfies those properties. So more formally, we can call these properties specification. And for example, it can ensure that the program is free of memory leakage and array out of bounds errors and so on. And for example, we can abstract the operation of a microwave oven into the following finite state machine and verify whether this temporal logic holds to determine if a system meets the specification. Well, this expression roughly means that for all successor states of the current state, where start is triggered, the micro oven will eventually reach a heating state. And after acquiring a basic understanding of what is model checking, let's move on to some fundamental concepts and symbolic notions. So due to the time constraint, I will only give a brief overview to help you form an impression. So the detailed definition will be included in the slides. Well, the finite state machine we mentioned earlier is formally called a crypt key structure, and which can be roughly understood as a automaton without accepting states. And it can be represented by 5 tuple. So whereas represents the set of states, and S0 denotes the initial states, and R is the transition relation between those states. Well, and AP represents atomic propositions, which can have 2 values, true or false. And atomic propositions can take various forms. So for example, in the early microwave oven example, whether the microwave oven is in the heating state can be represented by atomic proposition of heat. So each state has its corresponding atomic propositions, and this mapping relationship is described by L. So moreover, the crypt key structure can be more intuitively represented as a directed graph, as shown in the diagram. Well, just like directed graphs, the concept of paths also exists in a crypt key structure. For example, the path from this state to this state is a finite path of length 2, And another example is the loop between these two states, which forms an infinite path. And next, let me briefly introduce a type of temporal logic we mentioned earlier, called computation tree logic. So as shown in the diagram, the left side represents the crypt key structure we discussed earlier, which can be unfolded into tree structure on the right, known as a computation tree. To describe the properties of this computation tree, and we introduced two types of temporal formulas. A state formula describes the properties of individual states during computation, while path formulas describe the temporal properties related to paths. And here are the definitions of the two types of formulas, but we won't go into detail. So, however, it's important to note that these formulas can be connected using logical operators like conjunction or disjunction, or disconjunction, and can be modified by temporal operators like until or release to create more complex logical expressions. And after acquiring a basic understanding of temporal formula, we now introduce CTL formulas. So with the following specific definition, in this context, X, F, U, and R are related to temporal operators. While here XP means that the next state of the current state satisfies the atomic proposition P, and FP generally means that in the current state and all subsequent states, eventually some state will satisfy P. And GP means that in the current state and all subsequent states, P will always be satisfied. And U, which is an abbreviation of until, means that P must hold on until Q becomes true. So R, which is an abbreviation of release, means that after P holds, Q can become false. But if P doesn't hold, Q will never hold. And A and G here are referred to as path operators. And temporal operators and path operators can be combined. So for example, AGP means that for all paths starting from the current states, every successor state will satisfy the atomic proposition P. And additionally, the previous mentioned AG start implies AF heat is exactly a CTF formula. And it is also worth mentioning that all the CTL formulas above can be converted into the standard forms using EX, EG, and EU. And their semantics are as follows. So where MS satisfies F means that state S in the crypt key structure M satisfies the CTL formula F. And additionally, we can omit M and simply write S satisfies F. So which also means that state S satisfies the CTL formula F. And we can also omit S and only write M satisfies F, which means that all the initial states satisfies F. And after introducing all this background knowledge, we can finally return to today's main topic. And let's first clarify the goal of CTL model checking. So, in a short words, given a crypt key structure M and a CTL formula F, we need to verify. Verify that whether M satisfies F. The entire verification process can be broken into two steps. And first, finding out states of that satisfy F, and second, verifying whether the initial states is included in these states. And for the first step, the model checking book of Clarke mentions that there are two algorithms called check EG and check EU that can efficiently find the set of states that satisfies F. And however, today we will introduce another approach, which involves using a fixed point iteration to find out the states that satisfy F. First, let's intuitively understand what a fixed point is. So, in simple terms, a fixed point exists when there is a function tau that maps one set to another. And among all the input sets of function tau, there are some special sets that they will eventually reach a stable state that no longer change after being repeatedly mapped by function tau. So these stable states, sets are called the fixed point of the function tau. So, for example, as shown in the diagram, the set S0 keeps expanding after being repeatedly mapped by function tau, and eventually reaching a stable state. And this state is called the least fixed point. And similarly, on the right side, the set S0 can keep shrinking and eventually reach a stable state, and we can call this state we can call this set greatest fixed point. And next, we formally define the function tau. Well, notice that in this definition, monotonicity will be very different. Will be very important for us. And according to the following lemma, we know that one function tau is monotonic function. Is a monotonic function. So each output set is a subset of the original set, or a superset of the original set. So in other words, each mapping either expands the empty set to a least fixed point, or shrinks the universal set to a greatest fixed point. So here, false represents the empty set because no state satisfies false, and true represents the universal set because all the states satisfies true. And another very important theorem is Tarski-Canestas theorem, so which states the existence of fixed points. One tau is a monotonic function, so tau has both least and greatest fixed points, and that can be expressed by the expression as follows. So with the addition of another two more lemmas, we can derive an algorithm for finding the greatest and least fixed points. So these lemmas indicates the existence of two integers, I0 and J0, such that by repeatedly applying tau function on the set will stop changing after ith and jth iterations. And this ensures that we can always find the least and greatest fixed point of tau. So moreover, note that most model checking problems satisfy the condition required by the lemmas, such as the monotonicity of the function of tau and the finiteness of the set S. So therefore, in most cases, we can confidently use these two algorithms. Well, here are the detailed process of the two algorithms. The idea behind the algorithms is very simple. The LPF algorithm starts with the empty set and repeatedly applies tau, allowing the set to expand until q equals q prime. And on the other hand, the GFP algorithm starts with the universal set and repeatedly applies tau and shrinking the set until q equals q prime. So while you might be wondering how does the fixed point iteration algorithm relate to CTL model checking, so I can simply tell you that you can directly transform the CTL model checking problems into a problem of finding the least or greatest fixed point. Below the correspondence between CTL formulas and fixed points, for example, the first row shows that the set of all states that satisfy AF1 is equal to the least fixed points of the function tau z. So once we find this fixed point and verify whether whether the initial state S0 is contained with this fixed point, we can determine whether the crypt key structure satisfies the CTL formula AF1. And for more complex CTL formulas, we can decompose them into some smaller subformulas, and each subformula can then be matched with its corresponding fixed point in the table of correspondence. So now let me use this exist P until Q as an example to illustrate this process. And based on the corresponding relationships we just discussed, the form of the form of the function tau is as follows. And first, let's look at the crypt key structure in the top left corner. And we start with empty set, and after applying the function tau, the resulting set should include all states that satisfies Q or satisfies P, and also have a successor set that satisfies false. Well, in this diagram, only this set meets the condition. So we then take this Q prime set and the so we then take this Q prime set as a new Q set. So we repeat this process continuously. Each time we obtain a new Q prime set and replace and set this Q prime set as a new Q set. And after applying function tau for the fourth time, we notice that the set no longer changes, and at this point we have found the least fixed point of the function tau z. So, and since we know that the initial state S0 is within this fixed point, and we can conclude that the Kripke structure satisfies the CTL formula exists P until Q. And now we have completed the verification. So finally, let's summarize today's lecture. First, I introduced the concepts of formal verification and model checking. To introduce CTL model checking, I also covered the related knowledge of computation tree, and I then explained the goal and steps of CTL model checking. So finally, we use the fixed point iteration method to solve the problem of CTL model checking. And thank you for watching. Thank you very much.